Let's begin this unit by looking at a photograph of a railroad. The rails are made of steel. In between steel beams, there are gaps. What is the function of those gaps? If a steel beam changed length for whatever reason, then at the connection with the next steel beam, there will be a bulge, because the ends of neighboring steel beams push against each other. What might make a steel beam change its length? For an object similar to the steel beam in the railroad, we can say that when the object becomes hotter, its length increases proportionally to the temperature increase. A rod at temperature T0 has a length L0. At temperature T0 plus delta T, that rod will have a length L0 plus delta L. That additional length delta L is in fact proportional to the temperature change delta T. This is an experimental result. Delta L is a proportionality constant alpha called coefficient of linear expansion that depends on the material of the rod times the original length L0 times the temperature change delta T. Immediately looking at the dimensions of this expression, you can tell that the units of coefficient of linear expansion must be inverse degrees, since the Kelvin and Celsius degrees have the same width. You could express delta T in Celsius or in Kelvin. Also, if delta T was negative, which means a temperature decrease, then the object would shrink. Delta L would be negative. Mathematically, you could write that the final length is L0 plus delta L, that is L0 times 1 plus alpha delta T. If alpha is positive, then the material behaves normally in the sense that when the temperature increases, the object will get longer, and when the temperature decreases, the object will get shorter. Here are coefficient of linear expansion alpha for different materials. The range is not very large, but it spans about 3 orders of magnitude. If we now consider a more generic shape, so not necessarily a thin rod, then we need to account for the change in all linear dimensions upon changing the temperature. So we call this process volume thermal expansion. When an object becomes hotter, its overall volume increases proportionally to the temperature increase. If you had a cube at temperature T0, that would change its volume at temperature T0 plus delta T by an amount delta V. The volume would be V0 plus delta V. It's an experimental fact that this delta V is proportional to the temperature increase delta T. The proportionality constant is beta. It's called coefficient of volume expansion, measured in the same units. Again, just checking the dimensions. Beta multiplies the volume times the temperature, so the units must be inverse temperature. And this is actually related to the coefficient of linear expansion alpha that we've seen a moment ago. The length, width, and depth of the solid will all increase with the coefficient alpha. So you could write for the length L0 times 1 plus alpha delta T, for the width W0 1 plus alpha delta T, and for the depth D0 times 1 plus alpha delta T. So if you call the original volume V0, you could write V0 equals L0 W0 D0, length times width times depth, and the new volume would be length times width times depth. You can show by simple algebra that the volume LWD is going to be equal to L0 W0 D0 times 1 plus 3 alpha delta T. The higher order terms involving squares of delta T and cubes of delta T would be much smaller than the linear term in delta T, so we actually neglected them. That means that the coefficient beta of volume expansion is nothing but 3 times the coefficient of linear expansion. In other words, the 3 dimensions independently lengthen, each one with a coefficient alpha for that material. And in fact, we can check a table for volume expansion coefficients, and you can see that those numbers are exactly 3 times the values given in the previous table. Also, you can define the volume expansion of a liquid, because liquid lacks a definite shape, so you wouldn't be able to define a linear expansion for a liquid, of course, but there are also liquids listed here in this table. Here is an example. A 2-meter long thin bar made of aluminum whose linear expansion coefficient is 2.3 10 to the negative 5 inverse Kelvin stands vertically on the floor of a garage. The ceiling of the garage is 2.02 meters tall. By how many kelvins should the temperature of the bar be raised for it to touch the ceiling? First of all, we need to look at what increment in length are we trying to get. The increment would be 2.02 meters minus 2.00 meters, that is 0.02 meters. So the ceiling is just 2 centimeters away, and we are going to use the equation for linear thermal expansion, where we are given the coefficient that is 2.3 10 to the negative 5 Kelvin to the negative 1. So we could solve for delta T here and write delta L over alpha L0, that is 0.02 meters divided by 2.3 10 to the negative 5 inverse Kelvin times 2 meters. The units, of course, will be Kelvin because it's 1 over inverse Kelvin. If you crunch the numbers, you'll find that the answer is approximately 435 Kelvin. This temperature increase expressed in Celsius degrees would be, of course, exactly 435 degrees because Kelvin and Celsius degrees have the same width. To understand whether this is even physically meaningful, we can compare with the melting temperature of aluminum, which we can look up. That is roughly 660 degrees Celsius. So the temperature will be the room temperature plus this delta T. If it was a summer day and the temperature in the garage was 25 Celsius degrees, then the final temperature would be 460 Celsius degrees. That's below the melting temperature, which means that provided we were able to actually heat up the bar that much, it will still be a solid aluminum bar.